Last time we finished up our discussion of our soil forming factors, organisms, relief, and time. Any lingering questions, make sure you ask. So now we are moving on and thinking about how we then take those factors and the properties they impart to a soil and name the soil, classify it, give it some kind of category so that we can then communicate with others about the soil and its properties in sort of a shorthand way. Some of the terms we're going to use are definitely words you have not heard before. It's going to be a little bit of a foreign language, but these are the scientific terms, the scientific names for soils that are then used to convey information about the soil to other practicing soil scientists and natural resource scientists. So we're going to start with diagnostic features. These are things within the soil that we use to assign them to the category. Then we're going to talk about the categories. And in this class, we're going to just hit the very top level, the 12 soil orders. It's the broad groups. We'll talk a little then about some of the lower levels and how we narrow that down a little bit. But the ones I want you really familiar with are these 12 major groups of soils. To get into the group, we need to describe the soil first, understand its properties, and then use that to categorize. And for the purposes of classification, we do that at what is called the pedon level. A pedon is a representative piece of soil, is my simplified definition here. It's just a chunk of soil that's big enough to show you the main properties of the soil in an area. It's the three-dimensional unit, and if you take all of the pedons that are similar to each other in an area and draw a line around them, like this, that becomes what we call a polypedon, multiple pedons put together. And that polypedon then is a piece of the landscape, and that's sort of the individual. The polypedon, we say, well, we've got some Lososa soil over here. When we do that, we're talking about this volume of soil, this area of soil that is similar in its properties. We can't excavate that volume of soil to describe it, or else we wouldn't have any soil left, right? And it's just a huge amount of effort. So instead we are describing at the pedon level, and really what we're looking at is a soil profile. So just to keep terms straight here, the profile is this two-dimensional cross-section that shows us the face of the pedon. The pedon is sort of the three-dimensional unit that often we have sort of removed, and we're looking at the outside walls of that. But then we pick one face, which is the profile, when we do our description. Within that pedon, we then look for specific features, diagnostic features, and they're diagnostic, meaning we diagnose the soil using them to put it in a specific group. And there are basically two versions of these diagnostic features. At the surface, we have the epipedons. Epi, like your epidermis, is your skin. It's of the surface of your body. Epipedons are at the surface of the soil. The endopedons are subsurface. More commonly, they're called diagnostic subsurface horizons, and that's kind of a long name, but endopedons works, and it kind of gives you that contrast between the surface layers and then what's happening down below. So all of these soils pictured here have some kind of diagnostic feature, an epipedon or a endopedon. In fact, they all have some of both going on. And so we look at the combination and then use that to classify. For epipedons, there are several options, and I'm just going to give you the most common locally, the most relevant for the central coast of California. In other parts of the world, there are others that might matter a lot, but this gives you sort of at least a starting point. We don't have time to get into all of the options, but these are some critical ones to understand. The first one is the molic epipedon, and this is foundational for defining a lot of other epipedons, including some of the ones we're not going to get into. But the concept of the molic epipedon is that it's thick, it is dark, and it has a lot of carbon, and it's basic. It's the actual definition is in like 10-point font, 2 columns in a big book. It gets very detailed, but this is the general concept. Usually we're looking for at least 25 centimeters. Sometimes you only need 18, sometimes you only need 10. That's where it gets really complicated. But there's a thickness requirement. You need to have a decent amount of it. The colors need to be dark. We'll talk about soil color going forward. You'll see some examples in your lab this week of soil colors that are not quite as dark as the one image pictured here, but meet Moloch colors for being relatively dark. There's a base saturation, an actual chemical measurement that we take, and a carbon measurement. So there are a lot of criteria, but the idea is we've enriched this soil with carbon. The carbon has made it dark, and we've done it in a thick enough zone to really build up this horizon. Moloch epipetons imply fertility. They imply fairly rich soils for agricultural purposes or for plant growth. Next up, we have a pair, and I'm grouping them together, histic and folistic. And these are our organic epipetons, meaning they're not mineral material, they're organic material, O-horizons. Histic comes from the Greek word for tissue, and so it's made from tissues, generally plant materials that have degraded, and usually it's in a wetland setting. So we've accumulated organic matter. Histic is thick and wet. Folistic, think foliage, comes from the root for leaf, and so here we have a folistic epipeton that's much thinner, not saturated by water, it's just collecting on a forest floor. So an accumulation of leaf-type material on a forest floor, not as thick and not preserved by water. Instead, it's just got so much input that it kind of, in balance, we get a layer of organic material. So for the folistic, it kind of looks like this. There are actually thickness requirements that are also need to be met, but that's the general concept. And then one more epipeton, and that is the ochric. And ochric, it's basically the catch-all, it's the garbage can at the end of the classification scheme where you go through and say, is it Moloch, is it folistic, is it histic, is it etc., etc. And at the end, you say, well, no, it's not any of those. For everything else, there's ochric. Ochric just, by definition, it's at the surface, it's soil, but it doesn't meet other criteria. The implication is it's not thick and dark, it's not organic, it doesn't have these other properties, so it tends to be kind of light colored or thin, not a whole lot going on in the ochric epipeton. So those four, Moloch, histic, folistic, and ochric, are the four epipetons I want you familiar with. Endopetons. This is a very abbreviated list, and we're going to abbreviate more, but just to kind of give you an idea of the range. Argillic we are going to look at in much greater detail, well, slightly greater detail. And cambic we're also going to look at in a little greater detail. The others, I'm just throwing them out here to expose you to the range of possibilities. Natric is dominated by sodium. Spodec has iron or aluminum with organic matter. Oxic has oxides. Albic is like an E horizon that is whitened. Calcic has calcium carbonates. Petrocalcic cemented by carbonates. Durapans are cemented by silica. Not a lot of fun to dig through if you ever run into one. They're not uncommon in the Central Valley. So if you're from that part of the state and tried planting a tree and hit what felt like a rock but looked like soil, you may have met a durapan. Candic is an accumulation of highly weathered clays. So we've got a variety of things, and this is just a smattering. The actual list. Take soil morphology with me and you'll have a 7-page homework to work through all of the different diagnostic horizons and features. The two I want to emphasize, because they end up being very important for classification purposes, are the argillic, and then we'll get to the cambic next. Argillic, if you speak Latin or a Latin-based language, like I know in Spanish, the word for clay is arcilla, Arcilla. argilla comes from the Latin root for clay. So anytime you see argy, not to be confused with agri, which is like agriculture, but argy tells you something about clay. And in this case, it's subsurface accumulation of alluvial clay. And in this photo, it's down in this zone. There's also some iron moving around with it, and so we're building up clay. Soils are clay factories, right? With time, things weather into clay, and as that clay moves within the soil profile, it can accumulate in a zone, and that gives us the argillic horizon. It has more clay than the horizon above it, implying that we've increased the clay, things have moved down into this horizon, and there's evidence of clay movement. And that is generally like coatings of clay on sand grains or on particles. We call those clay films that show that the clay has actually moved. Not that it just happened to have a high clay zone, but that we've had movement of clay. So that is the argillic endopedon. The cambic is a weak endopedon. There are a bunch of other options, but if you get there to the end and you say, well, there's not much development, but there's some, then cambic fits that. Sort of like the ochric. For epipedons, you always are going to have one if it's soil material. For endopedons, it's not as required, but if there's development, then the cambic epipedon is kind of a catch-all. Things like color development, structure development, a little clay accumulation, but with not as much as you had in the argillic, those can all be enough to get a cambic subsurface horizon. So those two, know the concepts in a little greater detail, but it's just a taste of the possibilities. Take soil morphology and again we'll have some real fun with subsurface diagnostic horizons. So now we have this framework. We look at a soil pedon, we identify the diagnostic features, the epipedon and any subsurface endopedons. And then once we've got those all cataloged, we then use a system called soil taxonomy. If you're familiar with taxonomic keys in botany or things like that, you're going through and classifying based on a series of questions. We do the same things with soils. Questions like, is there a molic epipedon? Is there an argillic horizon? And based on those questions, we end up in one of 12 orders. These are the largest scale groups. There's quite a bit of variability within each one, but there is a common theme central to each of these 12. I would like you to be familiar with all 12. My challenge for you, get this list, write it down, copy it, and don't just look at it on the screen. That'll help you cement it in your mind, and then come up with some mnemonic device, a 12-word sentence that the 12 words each start with the same letter as one of these orders, so that you can just read off the sentence in your mind, write down the first letters, and then fill in to make sure you've got all 12. The other thing you'll note on this slide that I've done, each one of these has in green and underlined, in case you're colorblind, a 2 or 3 letter portion of the word, portion of the order name. Those highlighted elements are what get put in the actual soil name at the end, and I'll show you an example of that at the end of our lecture. But those are good to remember, because when you see a soil name, we don't say this is an inceptisol and it's all this. There's a lot that goes into the name, and so all you'll see is ept at the end. We use that little abbreviation. So those little 2 or 3 letters are the abbreviations for these orders. So those would be good to be able to identify. If you see a soil name, then you can immediately say, oh, that's an ultisol. Knowing what an ultisol is, you can then say a lot about that soil. We're going to talk a little about all 12. We'll do a few right now, and then we'll save the rest for the next video. But we're going to start with gelisols. Gelisols, think gelato. Gelato is frozen. These don't taste at all like gelato, but they are frozen. So very cold climates. They have permafrost near the surface. Permafrost meaning a part of the soil that never gets above 0 degrees Celsius. It's permanently frozen. They're not super widespread in the continental US especially, but you get up to high latitudes and very high elevations, and you can find a Gellisol. California is the only state in the United States with all 12 soil orders represented. And we don't have a lot of Gellisols, but there is one spot at the base of a glacier up in the White Mountains where they've gone enough years in a row to measure temperature and document that it does in fact have permafrost. So for us, it's at a very high elevation. I'll show you a map here. This is the map of Gellisols in the US, and they don't bother putting the tiny speck in California. Basically, it's Alaska. Most of Alaska is really cold, and so you get frozen soils. And in those frozen soils, you can get some cool patterns. I should go back and comment. All of these cool, crazy, mixed-up patterns, that's from freezing and thawing. We've got permafrost lower down, but up in the zone that freezes and thaws, ice, when it freezes, expands in volume a little, and it pushes things around, and it causes mixing. And so that mixing has created these really crazy patterns in this soil. And those same freeze-thaw processes result in these landscape-level patterned ground patterns that are creating these polygons from zones where ice is getting in and pushing things around and creating these features. So some kind of cool features and literally cold features in Gellisols. Next order are the histosols. Might make you think about the histic epipedon, maybe, hopefully. So histosols have histic epipedons, and histic epipedons are thick organic layers dominated or saturated with water during some part of the year. We've got a lot of water that is allowing this organic material to accumulate, and by accumulating all of that organic matter, we get a thick organic soil. So histosols are organic soils. They tend to be really light, low density because they're made of plants instead of rocks, so much lighter, much less dense, and most common in wet areas like wetlands. That water is what is allowing that organic material to accumulate. It keeps it from being degraded as quickly as would otherwise be the case. If you drain a histosol to farm it, suddenly oxygen gets in there that wasn't there when it was accumulating, and then microbes that use oxygen, they suddenly can see all this carbon and say, oh, look at that food, and we've got oxygen, everything we need to survive, and they can eat away these histosols. They just literally disappear into air. They are converted into carbon dioxide, much of that organic material. So they're preserved by water, take away the water, and that preservation disappears. There's a map of histosols in the US, and cold climates also help preserve them, but these are also pretty wet areas. Coastal areas, Everglades. There's a little green dot here if you're from the Delta region of California. San Joaquin, Sacramento River Delta has a pocket of concentrated histosols. And here, this person is actually going to burn this because it's organic matter and it's flammable. And this is a harvest site for fuel, but you can see a good wetland histosol exposed. Our third soil order are the spodosols. These are acidic soils, often in cool forests, often coniferous forests. They are characterized by leaching of organic matter with iron and aluminum. And as a result, you get zones like this. Below, usually they have an E horizon because of all this leaching, and you get these darkened and or orangey zones where the iron and organic matter is accumulating subsurface. Instead of moving clay around as much in these soils, we're moving other chemical constituents. Often these are in sandy soils that allows all of that movement to happen. In the United States, there's one spodosol in California, somewhere up on this area. Not a whole lot in our state, but we've got one. but the Pacific Northwest has a few. New England has lots and lots, and Florida has lots and lots. And those are both areas with a lot of sandy parent material and a lot of rain and coniferous forests. So you kind of all of those factors coming together. Common themes in these pictures: E horizon with the darkened layer below. Here that dark layer shows up really low on the horizon, very thick E horizon, but still a spodosol. E horizon, accumulation of iron and organic matter. All right, so that's 3 out of 12. Pause, mentally, literally pause the video, and when you do, mentally just think through these 3: gelisols, histosols, spodosols. Note down any questions you have. Go back and check your notes if you're confused about anything, and make sure you remember these 3 orders. All right, we're going to hit 3 more before we wrap up this video, and we'll get to the last 6 in the next section. The next one is andesols. Andesols form from volcanic material, volcanic ash or other ejecta most of the time. I think a good tool is to think Andes mountains. The Andes are volcanoes, andesols. The and root is actually from Japanese for dark, ando, because in Japan they have a lot of really dark andesols. So it's not actually because they're from the Andes, but if that helps you remember it, then that works. These are fairly recent volcanic activity. You still have to have that ash there. The ash will weather away, so it has to be relatively recent. In the U.S., that's mostly in the Pacific Northwest, coming down into the Cascades, Lassen Volcanic National Park we have up in this part of California. So we've got where we have active volcanoes, that's where we have andesols. And andesols, one of their common features is layering, because volcanoes erupt more than once often, and you get one eruption, deposits a bunch of ash, and the soil starts to form, and then the next eruption buries it with more ash, and so you get these stacks of soil material and layers of ash showing up partway through the profiles. All of these numbers and B's are telling you that each zone here is a kind of a mini soil profile in a new ash layer. So stacking up of ash. The ash itself is often fairly fertile, and you can have some pretty productive soils, but there are also some complications with ash that they're interesting soils, chemically speaking and geologically speaking. Next there are oxisols. Oxisols, think oxides. Oxidation, rust. Go back to that weathering process. And so we are accumulating oxides, and the reason they are accumulating is because these soils are so highly weathered that everything else is just gone, and what's left behind is basically a pile of rust. So highly weathered soils, they're mostly found in tropical regions because that's where we have enough precipitation, enough inputs from our factors of soil formation to get this level of weathering. Basically every other weatherable mineral is gone, and we've accumulated iron and aluminum oxides. So lots of oxides, low fertility because any nutrient in there, if you've leached away all of the other minerals, the nutrients don't stick around for very long. Our map of the United States oxisols is a close-up of Puerto Rico and Hawaii, and the U.S. Virgin Islands apparently have one or two. Tropical areas are where you're most likely to find them. California, we have one oxisol about there, and we formed it about 40 million years ago when we were in a tropical climate, and it got buried and uncovered. It still has all the properties of an oxisol, that it's sort of a geologic remnant, but it's an active functioning soil, has all the properties of an oxisol. It just happened to form 40 million years ago. One more soil order for this video are the vertisols. Vert, the name here comes from invert. The idea was these soils, they expand and contract, and as they do so, things mix a little bit. And it turns out they don't mix as much as they thought initially when they named them, but there's this inversion. Well, there's this expansion and contraction. There are these processes happening and volume changes. They're dominated by clay. You have to have lots of clay in these soils, and it has to be the right kind of clay. There are specific kinds of clays that when you get them wet, they bring water into their interlayers at a microscopic scale and they expand. And when they do, at the macro scale, the total volume of the soil increases. They soak up this water, expand, and the soil expands. When they dry, everything shrinks and you get cracks left behind. And so you have these changes in volume from wetting and drying, and that creates some very specific features within the soil. If you're going to try and build something on a vertisol, don't dig it out and get rid of it, but it is not a stable surface for any kind of structure, as evidenced in this image. Probably not the best place to build. There's another image that shows the surface cracks when things dry out. So we're talking big cracks, big volume changes. We have quite a few vertisols locally. On campus, on the right part of the P Hill, if you go up Stenner Creek Canyon, if you bike back there, there are pockets of vertisols that show up around campus and around San Luis Obispo. If you're out hiking and you look down at your feet and you see, usually in our area, they're almost black colored soils and get these big surface cracks. If you see those, you're probably on a vertisol. All right, so another chance to pause. We've made it through half our soil orders now. So pause the video, make some mental notes, think through what are andisols, oxisols, and vertisols. Make sure you've got a solid understanding on those. And with that, we will pause the video formally and wrap up our discussion of soil classification in our next segment.